Happy day, everyone. This is Orekoya Olusegun, Physics Mathematics Fundamental on YouTube. Please, before we go into today's topic, do not forget to like, share, subscribe. Click on notification button to have more of my video. Now, for partnership, this is my phone number and this is my OPay account so that we can reach to more people all over the world. Now, today we are taking a topic under mathematics, and that topic is ordinary differential equation using the non-exact solution method. Now, I've already done video on how to solve ordinary differential equation by homogeneous method and then by separable variable method. Please, you can refer to that, and also did another one on how to solve the ordinary differential equation by exact method. So today we are taking us on how to solve ordinary differential equation ODE by what is called the non-exact method. Now let's look at this question here. We are given this question, we are asked to solve. Now we are given y dx plus x squared minus x with respect to y. That's the y is equal to 0. Now, first thing I would like to do is to put this expression as a single letter in each case. So I'll write this expression before this dx as my n, and this expression before dy, I'll write it as my n. So I'll write this one now as n dx, then this one will be n dy. I'll put it as is equal to 0. Now, the next thing I'm going to do is to find the partial derivative of each of these expressions and see whether they are going to be equal or not. What I mean by that is that I'm going to find the partial derivative related to y if it is not the same thing as the partial variable of this function n with respect to x. If they are not the same thing, then that means this particular method requires non-exact approach. So what do we do concerning this? Now, the meaning of this partial derivative with respect to this one will be delta of this function n with respect to y, and that particular function n is y, which is delta y all over delta y, which is equal to 1. That is for this partial derivative delta y. Then I want to compare with this partial derivative of this particular expression here with respect to x, which is delta n with respect to delta x, and which is delta, our n here is x squared minus x. That is x squared minus x with respect to the variable x. And if I differentiate this, it's going to give us 2x minus 1. Because when I differentiate this one, I'll use this power to multiply. I use this one power to multiply, subtract. So minus 1. That is my partial derivative with respect to x here. So n x is equal to this expression I have here. Since what I have here is not the same thing as what I have here, that is, the partial derivative with respect to y is not the same thing as the partial derivative with respect to x, then we use the non-exact method. So what we are going to do is to find a special function of x, and that particular special function of x is normally obtained using the partial derivatives. So it's going to be the difference between this partial derivative and this one, then all over this function n. And what we have this partial derivative here is 1 minus the partial derivative here is 2x minus 1, then function n, which is x squared minus x. So I can simplify what I have here by opening that bracket. Minus times everything here will give us minus 2x plus 1 divided by x squared minus x. So this particular function of x can be simplified further. 1 plus 1 will give us 2. So we have 2 minus 2x divided by x squared minus x. So I can factorize 2 out here as 2 brackets. When you take 2 out here, that will be 1. When you take 2 out here, x will be left. Then divided by, I can factorize x out here. So when you take 1x out, remain 1x. When you take x out here, remain 1. Now if you look at what we have on top and what we have below here, we can make them to look the same way by factorizing -1 here out. So that means this special function of x now can be written as -2 bracket 1 minus x, then divided by x bracket, since I have factorized -1 out, this will interchange. That will be x minus 1 divided by x minus 1. So this factor that we have here, cancel this factor here. So the special function of this x now is equal to -2 over x. Now, our integrating factor in this wise now can be written as e raised to power integral this special function of x with respect to x, and then which is e raised to power, our special function now is going to be integral of -2 all over x dx. Now, if you look at this now, we have e raised to power. This -2 is a constant. We can take it outside the integral distance. So we are left with 1 all over x dx. From our standard integration of 1 over x dx is ln x. So this expression I have here will be e raised to power -2 ln x. And then when you are using a factor to multiply logarithm, that particular factor will be the power of the expression inside that logarithm. So what I have here now, our integrating factor now will be in the form e raised to power ln x raised to power -2. So now we can rewrite this one now in a way that we can be able to use what we are going to use to multiply this differential, the original differential equation, to be able to convert it to the exact method. So what we are going to do now, recall that if you are converting this initial equation to logarithmic equation, it's going to be x is equal to log of this number n to base p. So the same way with this one now. So what I'm going to have here is ln x raised to power -2 is equal to log of this I with respect to e. Now, which is same thing as ln I. So my integrating factor I now, because expression I have here is same as the expression I have inside this ln on both sides. The integrating factor will now be x raised to power -2. So I'm going to use this integrating factor now to multiply the original question given. So I'm going to have it as x raised to power -2 multiplying everything. That is y dx plus x squared minus x dy is equal to 0, because this 1 times 0 will give us 0. So now, what I have here now, if you use this to multiply this, you have x raised to power -2y dx plus, if you use this to multiply from the law of indices, x raised to power -2 times x raised to power 2 will give us x raised to power 0, which is 1, minus from law of indices, x raised to power -2 times x will give us x raised to power -1, then dy is equal to 0. So now the solution, this is what we have here now. We need to test it to know whether the expression that we have here is we can use exact solution method to solve it. So in a nutshell, I will rewrite this expression here again as my m, and this expression here as my n. So this will be m dx, and this thing will be n dy is equal to 0. So I'm going to do the partial derivative m with respect to y of this one, which is delta of x minus 2y with respect to y. And I'm going to also do that to this one. But let me check what I'm going to obtain here. So with respect to y here, when I differentiate this 1 times 1 using the differentiation, we hold this one as constant. So the constant x raised to power minus 2 remain the same. Then we differentiate y. When we differentiate y with respect to y, give us 1. So this gives us x raised to power minus 2. Now let me check for the partial derivative of n. So when we take partial derivative of n with respect to x this time around, is going to be delta of n. Our n now is what we have here, 1 minus x raised to power minus 1 with respect to delta x. Now, differentiation of a constant gives us 0. So, differentiation of this one now, we have minus 1 times 1 gives us plus. So, it's going to be x, then minus 1, that's also minus 2. We can see that the answer that we got for derivative with respect to x and what we got for derivative with respect to y, we got x raised to power minus 2 in each case. So these two now counterbalance this partial derivative with respect to x. Therefore, what we have here now is we can use exact solution method to solve it. So in order for us to have more space, please let me create a space here. Sorry about that. So I'm going to rewrite this one out as if that's where we are starting from. So our new ordinary differential equation we are going to deal with now, after we use integrating factor, is this: plus 1 minus x raised to power minus 1 dy is equal to 0. So since we know we can use the exact method, the solution will be in form of fx of y is equal to, we integrate each of these. So x raised to power minus 2 y dx plus integral star. I will tell us what I mean by it. Why do I have to put that star there? Then 1 minus x raised to power minus 1 dy is equal to c. The reason why I put this star here is this. When I integrate this one, if I see a term that appeared here also, I will pick one of those terms. The repeating term will be picked once. So now, this solution now, this special function solution of the ordinary differential equation, when we want to integrate with respect to x, we are going to add 1 here. That's going to be x raised to power minus 2 plus 1 all over minus 2 plus 1. Then with the factor y remaining as it is. Then we integrate this one too with respect to y. Since I don't have y here, integration of a constant will be with respect to that variable. So this will give us y minus, since there is no y here, this will give us y x raised to power. When we are integrating, this is x raised to power minus 1. So now, if I simplify this one now, I'm going to have x raised to power minus 1 y divided by minus 1. Which is seen as minus y all over x. If I do, I have simplified this one too. I'm talking about this expression. I'm going to have y minus y all over x. Now, since minus y over x appear here and here, I'll pick one of them and add it to this. So I'm going to add these two together now. So the solution of that differential or other differential equation will be what are the term that I have a minus y all over x, then plus y we say is equal to c. So this solution method, I mean this particular different solution is supposed to be expressed to the constant c. So this is the solution of the original ordinary differential equation that we started in. Thank you so much for giving me your time. Please do not forget to like, share, subscribe, and click on the notification button to have more of my video. Have a nice day. Bye.